Okay, hi everyone. So this is going to be another short video going over evaluation metrics. So it's the continuation of the lecture we did last week, where we covered training test sets and different types of blocking and generalization. And what we now want to do is do a quick overview of different evaluation metrics. For most of you, parts of it will be a recap from other classes you've taken already. There's going to be a few distinctions here where we'll focus on. So I'll try to highlight those rather than rehashing all the different metrics. So overall, here's where we are right now, right? We're going to build a bunch of models on our training set, and then we'll predict on the test set. And now we have to calculate the evaluation metric that we care about. So we want to do two things here today. One is go over a few of the commonly used evaluation metrics, and then two is figure out what metric makes sense for the problem that we are working on. So I'm going to do a lot of the first thing today, and then we'll do the second one mostly in class on Tuesday. So here's the first thing to sort of keep in mind, right, is we built a model on the training set, and now we have a validation or test set, and we make a prediction. In general, in pretty much most models we're going to use in machine learning, the predictions are never 0-1 predictions. We are not, the models that we use don't generate 1 or 0. They generate some score, as we've covered in class. That score sometimes ranges between 0 and 1 in cases of logistic regression or decision trees, or but sometimes it's not bounded. So like support vector machines will give you a score that's distance from the margin. That could be a large positive number or a large negative number. For now, we're going to kind of assume 0 and 1. Bounded between 0 and 1 does not, as we talked about in class, does not make it a probability. It's just a scaled score between 0 and 1. And we shouldn't treat it as a probability unless we have tested it for calibration and make sure that it's actually calibrated probability estimate. So this is one typical, not typical, this is an example of a score distribution that you might get from a neural network or a logistic regression or a random forest, where you've got score distribution, histogram, and that is the output of the model. As far as the model is concerned, you are done now. And so now it's our goal to figure out how correct is the model. And so the first thing we do in most of the metrics we're going to use is remember that predictions are often scores between 0 and 1. And first thing we do in order to calculate metrics like accuracy and precision and recall, we first turn them into 0 or 1. We classify by selecting a threshold. And the thing is here, the thresholds that we select, something to remember about thresholds is thresholds are somewhat arbitrary because they're not calibrated. Thresholds are also not comparable across models. So a 0.6 in a logistic regression model might not be anything close to a 0.6 in a different logistic regression model or a different random forest or a different neural network. So we can't really compare things unless they're calibrated. And that's something just to keep in mind. So we're going to cover a couple of ways of kind of selecting this threshold. But once we've selected that threshold, the 0-1 turns into, the score turns into a hard classification, 1 or a 0. That we can then turn into what's called a confusion matrix, right? So most of you hopefully have covered this before. So this sort of tells us what the actual prediction is, a 1 or a 0, and what the prediction is and what the actual class is, right? And so we've got true positives, true negatives, things that the model was correct about, and false negatives and false positives, things that the model was wrong about. Once we have this confusion matrix, we can now calculate a variety of metrics, evaluation metrics based on that. So here's a laundry list. Accuracy is probably the one you have seen very often. And accuracy is fairly simple, but also not very useful. So we will rarely, if ever, use accuracy as a metric in most real problems. And it's primarily because most of the problems we're going to deal with are not going to be 50-50 positive negative. They're going to be skewed problems, and also where a positive may not be equally important as a negative. So accuracy is a good thing to know about, but unfortunately, we're not going to use that very often. But accuracy is all the correct decisions that are made by a model divided by all the decisions that are made by the model, right? So basically by thresholding it, so it's important to keep in mind is this confusion matrix is not an absolute that's given to you by the model. This confusion matrix is just one of many confusion matrices you can create if you pick a different threshold. So for this confusion matrix, the accuracy based on k being the threshold, let's say k is 0.2, everything above a 0.2 is 1, below is 0. These are the 4 decisions that are made. And so accuracy is the sum of the correct decisions, these two, true positives, true negatives, divided by the sum of all the decisions, right? And so that's the basic we've seen this metric before. So now let's go to some more useful ones. And we'll cover in class later again. One of the things to think about accuracy is you could have 99.9% accuracy and the model be completely useless. And think about why. We'll cover that, in class, right? Second, precision. Precision is so some synonyms for you, right? Another term for precision in different disciplines, other disciplines, is positive predictive value, PPV. You're going to hear that a lot in public health and EPI. And so positive predictive value is another term for precision. And that is of all the things you classified as positive, all the predicted yeses, these, how many were you correct about? Right. So the correct ones were true positives. Your total predicted ones or yeses were true positive plus false positives. And so that's your precision. And it's important to kind of think about, what does that mean in practice, right? So it means in practice is I thought these students were high risk of not graduating. I predicted them as ones at risk of not graduating, but I was right about 60% of them. Well, then my precision is 60%, or my positive predictive value is 60%. And so it's really designed for problems where we are predicting some, the things we care about are getting the precision, the ones right. So we predicted these as ones and we were right about some percentage of that. The other metric that we often care about is called recall. It's also known as sensitivity. And there we are concerned about, think of it as coverage, right? And so precision is, let's say I'm really sure about this one, my model is really sure about this one person who's not going to graduate on time. And my model says that one is a 1. And let's say the model is right. Well, it has 100% precision, but maybe there are 600 students that are not going to graduate on time. So I'm being precise and have high precision, but I've missed out on most of the students who need help. So recall is sort of looking at that dimension, and recall is saying, of all the people, for all the students who are actually positive, so true positives plus false negative, these are the actual positives, how many did my model get right? Right, that's true positive. So that's called recall. And recall in some ways, if you think about it in the policy terms, is related to being effective. Like how many people who needed help did I actually help? Did I get right? Versus precision is about more efficiency. How many people did I help? What percentage of those actually needed the help, right? So they're sometimes often trade-offs in those. Then there are many other metrics you can calculate. These are going to be the common ones. There are many other metrics you can calculate based on this confusion matrix. Another one is specificity that you may have heard about, which is the true negative rate. What I actually find really useful as a really good cheat sheet is this diagram, this image from Wikipedia, one of the few useful things on Wikipedia. And this is your confusion matrix right here. And it's useful for 2 things. One is it gives you synonyms for these different metrics that you may read in different papers in different disciplines. So for example, over here, recall is the same as sensitivity. It's the same as a true positive rate. True negative rate is the same as specificity and selectivity. Fallout is the same as FPR. Precision is the same as PPV. So that's useful to know these terms, and that's one reason this is useful. The other one is you can look at a confusion matrix and then also figure out what formula, how do I calculate them, right? So we just covered precision, right? Or actually, the first one we covered was accuracy. Accuracy is number of true positives plus true negatives divided by everything, right? And then precision is over here. True positives divided by all the ones I predicted as positives, right? So those are these two. And same for recall, we get true positives divided by all the actual positives. The other thing to keep in mind is that in different papers and different books, you're going to see these two axes sometimes flipped. Sometimes this is predicted and this is actual or true, sometimes other way around. So don't get too tied up with the rows and the columns. Just kind of look at the matrix and figure this out. So this is a really good cheat sheet. Another metric you're going to notice that some of you were using in your proposals is F1 score. And F1 is also reliant on a threshold, right? Anything based on a confusion matrix relies on a threshold, because a confusion matrix, again, is based on a specific threshold. And F1 is this, it combines recall and precision. And it's sort of used mostly in cases where you don't really know, you want to sort of combine the two things. In practice, actually, for a lot of policy problems, it's not used very often because we'll cover that actually a little bit later. But it exists as a metric, and so do many false discovery rate, NPV, FOR, all sorts of things. So those are kind of the primary metrics that are threshold based. But now the question becomes, what is the trade-off between these precision and recall? We're going to use those most often, and how does it change as you select thresholds? So one thing you're going to see, I'm going to actually cover this first, right? You're going to sort of actually let's do before we go in there. I'm going to switch to you've often seen sort of something like a precision recall curve, right? Where you've got precision here and recall here. And what you see sort of a typical precision recall, the theoretical curve looks sort of, something like this, where each point here is a different threshold. Right? So let's say we look at this. This is the point where typically our threshold is really high, where we're saying anything above a 0.9999 is going to be classified as a 1, everything else is 0. That means I'm going to classify very few things as 1s, which means most likely for a good model, it will have very high precision, but low recall. Right? So this might be the 0.99 threshold. Let's say then I go to a 0.9 threshold. Well, that's going to reduce my precision most likely, because I'm going to call more things 1s and I will be less right as a percentage, but my coverage or recall increases. I go down, maybe this is 0.8, 0.7, 0.6. And so as I go lower and lower my threshold, my recall goes up because I'm saying yes to more and more things, but my precision goes down because I'm adding more negatives to my predictions. So this is a thing that you've seen before. We're going to actually not use this very much because there's a couple of problems. What we need is a third dimension, which is this threshold. But we also need another dimension, which is in a lot of real problems, especially the type of policy problems we're talking about. The thing that we control is not the threshold, not the precision, not the recall. What we actually control is what percentage, what number of people are we intervening on? What number of facilities are we inspecting? What number of students are we intervening on? What number of voters? What number of bills? And so what we're going to do is use a slightly different version of this graph. It has the same information. It's just designed to be a slightly different way to express the policy menus that we're providing. And here's how that's going to work. What we're going to do is we're going to first take our test set, right? So example number 1, 2, 3, let's say up to 100. My model will predict a score. Let's say the first one gets a score of 0.6, 0.7, 0.2, 0.6, and 0.9. The next thing I'm going to do is I'm going to sort them, right? Just like I do to calculate precision. So we'll sort them in descending order. So maybe, example number 100 comes first with the highest score, and then the next score is 0.8, 0.8, 0.76, 0.74, 0.02 is the lowest one. So now, and maybe this is example number 4, right? So I've now got this sorted list. What I'm now going to do is use my x-axis to say, what if I come down on this list? What if I take the top 1% of the population in this list, right? So in this case, I'm going to take the top 1% of, maybe because it's only 100, I'm going to take this one and say, what is my precision now? So let's say this actual label for this was a 1. Well, my precision is 100%. And so, and let's say the total ones in this data are 20. So what's my recall? Well, 5%, because I have one true positive divided by total true positives are 20, so it's 5%. So if I go back to this one, if I took the top 1% predictions of this model and made 2 axes, one for precision and let's say, one for recall, the recall for this is 5%, right? And the precision for this is 100%. So now this is the same point. If I was doing a precision recall curve, this would be right here, right? Somewhere, if it is precision and recall, this point would be 5% recall and 100% precision. So it's 100 and then 5 here, right? So, but now my x-axis is really I took the top 1% of the predictions of my model, and let's say I intervene in them. This one student or one bill, I would be right. So precision would be 1% and recall would be 5%. Now let's move to, what if I do that for the top 2%? What happens then? Well, if I go back here, the top 2% is this. And this is true label is 0. So what's my precision now? Well, 50%. Because at this point I've said yes to 2 predictions, and I'm right about one of them. And what's my recall? It's still 5% because I still have one example that I got, that one true positive, right? So now my precision has dropped to 50%, and my recall is still at 5%. So then so this threshold, then I go 3% and 4 all the way, right? So what's going to happen is I'll have some precision and I'll have some recall. As I go down further and further, my recall has to go up, right? And where does my recall end up? If I said yes to all of the examples in my test set, then my recall by definition is 100% because I've covered all of the positive. So my recall is going to go up to 100% eventually. Where does precision end up? What's the last point over here? Right? So if I said yes to, let's go back to this one. Right? If I said yes to everything, all the predictions were 1s, well, how many am I right about? What's my precision? Well, it's the base rate. What's my prior here? And that's 20%, right? We had said 20 of them are positives and 80 are negatives. So the last point here is going to be my prior or my prevalence, which is going to be by definition 20%. So precision curve will end up here, and recall curve will go up there. And so that is basically another way of representing the precision recall curve. But it gives you, so let's go back to the slides, right? If we go back to the slides, here is a version of that curve, right? Where the x-axis is the percentage of population in descending order of risk that your model has produced. And you're saying, if I look at the top 1%, precision recall, 2, 5, 10, 20, 30, 40, 50, 60. What this is a really good way of providing a policy menu, right? What this says is, if you use this model and you use it to intervene on, let's say, the top 10% of what the model is predicting, your precision will be about 95%. So if all the people you intervene on, actually 97 something, right? 97% of them will actually be high risk, will actually have outcomes that we don't want. And your recall, somewhere about here, right? So So if we look at, here's where the line, we're drawing at about 10%. So let's draw this line. So we're going to go to 10% intervention. I'm going to try to draw a straight line, which I can't do. So its precision is about actually 85%, I'm sorry. And recall is about 75%. So we're going to, the policy menu says, if you intervene, if you have capacity to intervene on 10% of the people and you use this model, in the top 10%, 85% of them will actually be high risk, and you will capture your coverage, your recall will be 75% of all the people who actually need the help. If you intervene on 30% of the people, you will lose in efficiency or precision. Your precision will be 35%-ish. So for all the people you intervene on, 35% will actually be at risk of the outcome you're predicting, but your recall has gone up to about 90%. So you're getting better coverage, better recall, you're being more effective at the cost of efficiency. You're being less efficient. If you really want to help everyone, then you're gonna, and this model says, well, in order to get to recall of 100, you're gonna have to intervene on about 95, 96% of the people. That's gonna be lower efficiency with a pretty low precision, but you get effectiveness coverage. So that's the trade-off. And so this is a better way, we found this type of menu, this type of graph is really useful to show policymakers or people who are allocating resources, and gives you a trade-off of, if you intervene on this many people, here's your efficiency, here's your effectiveness and coverage, precision, recall, positive predictive value. And then as you move forward, it allows you to look at the trade-offs. What you're going to sort of see is, this is one model, right? So if you're comparing different models, you might have another model that looks like this, right? And or in the precision curve, you might have another model that looks like this. And so what's useful to see is, if you're intervening on 10% of the people right here, the blue model is better. But if you're intervening on 20% of the people, if your capacity to intervene is 20%, then the green model is now better. And that's sort of the trade-off we want to look at. And that's why we've been, we're going to ask you, like, what metric do you care about? What is your intervention capacity? Because if your intervention capacity is 50%, this model is much better because it's twice as efficient and has better recall. But if your intervention capacity is only 5%, then the blue model is much better. And so it's not the same model that universally good for every intervention capacity. And that's something we're going to ask you to do, to think about for your project. The model you select will not be a generic model that's generally good, but it has to be good for your problem and your intervention capacity. And this is one type of graph you can use to communicate that those choices to the people who are making these allocation decisions. So we're going to ask you to plot this graph in your pipeline and for your projects, and in a couple of weeks in the templates we give you. This is the graph we're expecting. I'm going to call it precision recall, and K, where your K is your percentage of population. So in most of your projects, think about what metric makes sense, right? So if you're going to say, I'm building a system to alert ACLU on which bills are going to pass, and they're going to intervene on the 5%, they can intervene and do something about 5% of the bills, then what is the metric that you care about? Is it precision at 5%? What about for students? If this school can intervene on 20% of the students in 9th grade, how do you, what's the metric? Is it precision at 20%? And then the other thing to think about is, what's the relationship? If you fix 20%, what's the relationship between precision and recall? What happens there? So that's something to think about. We'll cover that in class a little bit. Other thing, right? So the nice thing about this graph also is where these lines end, right? Recall has to end at 100. Precision ends at, the baseline that we talked about, the prevalence. If 5% of your students do not graduate on time, then this precision line has to end at 5%. So it's a really good sanity check. If you build your models, run it on a test set, and the last point on this graph is not the prior in your data of ones, then there's a bug somewhere. So it's a really good way to check if you're doing something right. You should at least have these numbers right. Okay, last metric we're going to cover quickly. This is the ROC curve. Right? Most of you have used it or seen it. Receiver operator characteristic curves. Don't ask me where it comes from. Comes from the days of world wars and from radars, where the radars, the receiver, each radar had this calibration curve of true positive rate and false positive rate. So that's the history if you want to read up. But what this graph is, people use it for is again the same idea. It's this precision recall type thing, except it's normalized, so it kind of goes from 0 to 1. You can have, different models will produce different curves. And here's the nice thing to kind of, the AUC we normally look at, the area under curve, it's often this area under the curve of this ROC curve. And what it's really measuring is the area under curve, for this AUC is what it really is. It's saying, it's going to be 1 if you have perfect, the perfect graph is going to be like this, right? It has 0 false positive rate and 100% true positive rate. And that basically means that all the ones in your data, all the one have been predicted to be above all the zeros. So if your predictions put all the ones above all the zeros, then you have area under this curve is going to be 1, right? Perfect prediction. If it's the opposite, if all the ones are below all the zeros, if your model is sort of completely reversed, it's going to have 0 area under the curve. So the best model is 1, the worst model, horrible model, is 0. A random model is going to be 0.5, right? This line, this black line. So what ROC is a area under curved ROC is really a good way to quickly tell, is your model doing anything better than random? If it's 0.5, then it's random. If it's below 0.5, it's worse than random. If it's above 0.5, it's better than random. So it's a quick sanity check. But area under curve kind of treats this entire range equally. So this range that we talked about right here, AUC says, oh, that the entire range is about the same. I care, any prediction, doesn't matter where it is. If it's flipped, I'm going to count it the same way. If a 1 is below a 0, then it's a mistake, and I'm going to penalize it equally. Doesn't matter where it is in this range. And so if you care about the entire range of operation of your model, then AUC is a good metric. But if you care about just this space right here, the top 5%, the top 1%, or between 10 and 20%, because you don't know your intervention capacity, AUC doesn't really work, right? Because if you really only care about this space, so you might have to modify the metric. You can, instead of precision at K, you might sort of have area under curve between 1 and 10%, or 0 and 10%, if you're trying to think about it. So we rarely use AUC as a metric in problems where we have a concrete intervention capacity. We tend to use precision or recall at kind of a specific intervention capacity at K. But AUC ROC is still a useful metric to kind of get a general sense of the model performance. Yeah, so this is an example actually for real curves. I just wanted to kind of show real curves, precision recall curves, K curves are not going to be, as smooth as we drew over there. They'll be bumpy because there'll be noise, especially in the beginning, because your K is small and there's more variance in the models. And so we'll go more into that a little bit later. Yeah, so that's hopefully useful. Hopefully a lot of it is recap. The main things to take away here are, don't report a metric without a threshold, because it doesn't mean anything. So if you tell us the precision of my model is 60%, that doesn't mean anything, because you can adjust the threshold to make it 60%, and it doesn't tell me anything about. So you have to say, when looking, my threshold is 0.6 or my threshold is 10% of the population, and my precision is 60% on that. My recall is 20%. My accuracy is 54%. So that's something to keep in mind. The other thing is never, ever use the function .predict in scikit-learn. And we've covered that in class, but just again, never, ever, ever use that. It's a bug. It assumes a 0.5 threshold and hides that from you, which means you make a lot of mistakes assuming it's 0.5. There is no reason to ever use 0.5 as a threshold. It's not a probability. Even if it was a probability, the priors are not 50-50. Most of these are skewed problems, so be careful. Same with accuracy. You're rarely going to use accuracy as a metric. We'll cover that in class. And the last thing to keep in mind, which we'll keep repeating, is for your project, for your problem, think about what metric really matters. And the metric is really, what are you trying to achieve? Efficiency, effectiveness, um, um, and what resource capacity do you have? How are you going to intervene? So if your capacity is 10%, then your metric has to sort of say, how well have I allocated this capacity? Later on in a few weeks, we'll actually add some metrics that are going to be based on the bias and the fairness of your models. So disparity in certain metrics. So don't get too tied to the metrics we're covering now. We'll come back and add some more. But this was hopefully a quick reminder of some of these metrics that you've probably already covered. And then the precision recall K-curve as a policy menu is something we're going to keep coming back to as we do our work. So yeah, that's it. So hope to see you all in class on Tuesday.